Imagine art not just mimicking nature, but being generated by systems that truly grasp nature's deepest, most intricate patterns. That's precisely where we're headed today. We're taking a journey into something called fractal hybrid AI image generation, a fascinating field where, the ancient mathematics of fractals meets the cutting-edge power of artificial intelligence. It's where art, nature, and tech collide in truly surprising ways.
Absolutely. Our mission today is really to unpack this convergence for you. We'll explore how these systems actually work, the incredible, sometimes really strange new visual forms they create, and also the significant challenges researchers are grappling with. And these range from the purely technical hurdles to, well, the more profound questions of ethics. You're essentially getting a curated shortcut to understanding this burgeoning domain, straight from the latest research. We'll try to give you clarity without drowning you in jargon.
Perfect. Sounds great. Let's dive in. By the end, you should have a really solid grasp of this whole emerging field and why it actually matters. Okay, let's start right at the beginning then. Fractals. What are we actually talking about when we say fractal? Is it just a cool pattern, or is there some kind of deep mathematical idea behind it that AI can really latch onto?
That's a great starting point. Fundamentally, fractals are intricate, often irregular, and infinitely complex patterns. They really break away from the smooth, traditional shapes of, say, Euclidean geometry. Think endlessly detailed. Their defining characteristic is something called self-similarity, or maybe a more technical term, scale invariance.
Self-similarity. Oh.
Yeah, it means if you zoom in on any part of a fractal, that small piece will look remarkably similar to the whole thing. It doesn't matter how much you magnify it. It just keeps its rough or detailed appearance at absolutely every scale. Mm-hmm. Think about a coastline, for example. But, unlike a perfect circle, which would look flat if you zoomed in close enough.
Right, it smooths out.
Exactly. A fractal coastline just keeps revealing more and more jaggedness, more detail as you get closer. It never simplifies into a smooth curve. It just endlessly discloses new intricacies. This visual recursion is what makes them so captivating and mathematically rich too. And what's really fascinating is how this incredible complexity often emerges from surprisingly simple recursive rules.
Recursive rules, meaning like step-by-step instructions.
Precisely. These are procedures where the same basic step is just repeatedly applied to build the entire elaborate structure. It's like a tiny instruction leading to this vast, detailed universe. And mathematically, this leads to something called a non-integer fractal dimension.
Okay, that sounds complicated. Non-integer dimension.
It does sound a bit weird, yeah. But unlike a line, which is one-dimensional, or a square, which is two-dimensional, a fractal's dimension is often a fraction. This fractional number is basically a measure of its complexity or its roughness. It quantifies how densely it fills space, which is just totally different from how we measure traditional shapes.
Okay, that makes a bit more sense. So what are some of the most famous examples, the ones that really show off this recursive elegance and make people go, wow, what is that?
Oh, there are some absolute classics. The Mandelbrot set, for instance, is probably the most iconic fractal. It's famous for its incredibly complex boundary. You generate it by iterating a really simple math function, Zn plus 1 plus 1, 2 plus Cu, starting with Zeerdol. Then you just plot all the C values where the result stays bounded, meaning it doesn't shoot off to infinity when you keep applying the rule.
And that simple rule creates that intricate shape.
It does. And what's truly remarkable is its role as a kind of map for a whole family of related fractals called Julia sets. Julia sets are generated for a fixed, complex C value, and they consist of all the starting points whose orbits also remain bounded under that specific C. The really profound connection is this. A Julia set is a single connected piece if its corresponding C value is inside the Mandelbrot set.
And if it's outside?
If C is outside, the Julia set shatters. It becomes disconnected like scattered dust. It's an amazing visual link between the two. Beyond those, you have famous recursive constructions like the Sierpinski triangle. You get that by repeatedly cutting out the middle triangle from an equilateral triangle.
I think I've seen that one.
Probably. Then there's the Cantor set, which comes from an even simpler rule. Just keep removing the middle third of line segments. You end up with a set that has 0 total length, but paradoxically an infinite number of points.
Whoa, okay, that's mind-bending.
It really is, and maybe one of the most beautiful is the Barnsley fern. It stunningly shows how just a few simple transformations, like shrinking, rotating, and shifting applied over and over, can generate incredibly complex and natural-looking forms. It looks strikingly like a real fern frond.
That's incredible to visualize.
Yeah.
So how are these patterns actually built? Like, how do computers play them into existence using these recursive mechanisms? What are the practical techniques?
Yeah, their creation relies on some pretty precise formal methods. One of the most fundamental is something called iterated function systems, or IFS for short. An IFS is basically a mathematical framework. It uses a finite set of contraction mappings. These are functions that pull points closer together, usually involving scaling, rotation, and maybe translation.
Contraction mapping.
Yeah, they shrink things down. And these mappings are used to generate a really wide class of fractals. The elegance comes from what's called the Hutchinson operator. It's a bit technical, but it formalizes that self-similarity idea. It maps a set to the union of its images under each of those little transformations. The fractal itself emerges as the unique stable shape, the attractor of this recursive mapping process.
So the shape sort of settles into existence through repetition.
Exactly. And a really popular and intuitive way to see these IFS attractors is the chaos game algorithm. You basically start with a random point on your screen. Then you repeatedly pick one of the IFS transformations at random, apply it to your current point to get a new point, and plot that new point. You do this thousands, millions of times. And amazingly, the plotted points converge and trace out the unique fractal structure, like that beautiful Barnsley fern. It seems random, but order emerges.
That's wild. So randomness creates the pattern.
In a guided way, yes. In contrast, for fractals like the Mandelbrot and Julia sets, the main visualization method is the escape time algorithm. For each point or pixel on the screen, it applies the generating function, cisneatolar plus cnews, for instance, over and over again. Then it colors the pixel based on how quickly the result escapes a certain boundary, how fast it zooms off towards infinity, or if it stays trapped, bounded within a set number of iterations. This simple principle creates those incredibly vibrant, detailed fractal images we often see, with all the swirling colors representing different escape speeds.
And we really should give a nod to Benoit Mandelbrot here, right? The Polish-born French-American mathematician.
Absolutely. Huge debt to him. He didn't just coin the term fractal in the 70s, he truly popularized fractal geometry. He showed everyone how these seemingly complex, rough shapes were actually everywhere in nature.
Like coastlines, clouds, mountains.
Exactly. Branching trees, snowflakes, river networks. He brought these forms into the mainstream and argued that a new kind of mathematics was needed to describe the world around us more accurately, more beautifully than traditional Euclidean geometry ever could. His work really kicked off this whole field.
Okay, fascinating stuff. Now let's pivot. Let's talk about the other half of this equation. If fractals give us this language of self-similarity, this mathematical blueprint for complexity, what about the AI that's learning to speak it?
Right.
What exactly are these deep generative models? How do they work as this sort of creative engine for AI going beyond just analyzing data to actually, creating new things?
Right, so deep generative models are a class of algorithms specifically designed to learn underlying patterns and structures from vast amounts of data. And crucially, they then use that learned knowledge to create new synthetic data images, text, music that looks statistically similar to the data they were trained on.
So they're not just classifiers, they're creators.
Exactly. It's a huge leap. They actually synthesize novel content. And in this rapidly evolving space, three main families have really risen to prominence. Each has its own distinct way of working, its own strengths, its own weaknesses. They offer different trade-offs, really, in this quest for generating realistic and diverse outputs. First up, probably the most famous early ones are generative adversarial networks, or GANs.
Ah, yes, GANs. Ian Goodfellow, right?
Yeah.
Around 2014.
That's the one. A really pivotal moment for generative AI. GANs work using two competing neural networks. You have a generator, which takes random noise as input and tries to create fake data, like images. And then you have a discriminator, which acts like a detective. Its job is to look at both real images from the training set and the fake images from the generator and try to tell them apart.
So they're playing a game against each other.
Exactly. It's often described as a zero-sum game or a minimax game. The generator constantly tries to get better at fooling the discriminator, producing more realistic fakes. The discriminator constantly tries to get better at spotting the fakes. Through this competition, both networks improve. The big takeaway with GANs: they are fantastic at producing exceptionally sharp, often incredibly convincing images. They frequently achieve state-of-the-art photorealism. And another plus, once they're trained, generating new images is usually very fast.
But there are downsides.
Oh yes. The big catch is that GANs are notoriously unstable and quite difficult to train effectively. They often suffer from a problem called mode collapse.
Mode collapse.
Yeah, that's where the generator kind of gets stuck in a rut. It finds a few outputs that consistently fool the discriminator, and it just keeps producing those, or very slight variations. It fails to capture the full diversity and variety present in the original training data. Getting them to learn the whole distribution is tricky. Okay, so moving on, we have variational autoencoders, or VAEs. These were co-invented by Diederik Kingma and Max Welling back in 2013, actually just before JANs burst onto the scene. VAEs work differently. They combine a basic autoencoder structure that's an encoder network that compresses data and a decoder network that reconstructs it with a probabilistic framework.
Probabilistic, how so?
Well, the encoder doesn't just compress the input data into a single point. Instead, it maps the input data to the parameters, like the mean and variance, of a probability distribution within a continuous probabilistic latent space.
Okay, so the latent space isn't just points, it's fuzzy areas.
Kind of, yeah. Think of it as a compressed concept map where similar inputs map to nearby distributions. Then, the decoder takes a random sample from that distribution in the latent space and tries to reconstruct the original input image from that sample. There's a clever mathematical trick they use called the reparameterization trick, which is crucial because it allows the whole system to be trained using standard backpropagation, even though there's this random sampling step involved.
And what are VAEs good at?
Their main strengths are that they tend to be much more stable to train than GANs, and they excel at learning a really well-structured, smooth, latent space. That concept map is often very coherent. This makes them fantastic for tasks like smoothly blending between different concepts, like morphing one face into another, or performing semantic interpolation between images. You can navigate that latent space meaningfully.
But the image quality?
That's the trade-off, typically. The images generated by VAEs are often blurrier and less crisp compared to the best GAN outputs. This is partly due to the averaging effect inherent in their reconstruction loss function. They prioritize smooth representation over pixel-perfect sharpness. And then the most recent major players are the denoising diffusion probabilistic models, or DDPMs. These have really taken the field by storm in the last few years. Diffusion models operate through a two-stage process. First, there's a fixed-forward diffusion process. This involves taking a clean image and gradually adding small amounts of Gaussian noise over many steps, until eventually it becomes pure, indistinguishable noise.
So you deliberately destroy the image?
You do, in a controlled way. But then comes the clever part, the learned reverse diffusion process. This involves training a neural network to undo that noising process. Starting from pure noise, the network iteratively predicts and removes the noise added at each step in the forward process, gradually denoising the sample back into a clean, coherent image.
So it learns to reverse entropy, basically.
In a sense, yes. It learns the path from noise back to structure, and the results. DDPMs have demonstrated truly state-of-the-art performance in image synthesis. They excel in both sample quality, often incredibly realistic and detailed in diversity, frequently surpassing even the best GANs. Plus, their training process is significantly more stable than GAN.
Okay, there has to be a catch.
There usually is. Their primary weakness is the inference process actually generating an image once the model is trained. It's slow and computationally expensive. Because generating just one image requires running the learned denoising network sequentially for many, many steps, sometimes hundreds or thousands. This makes real-time applications a significant challenge compared to, say, JANs. So yeah, if we try to connect this all back to the bigger picture, it's clear there's no single best model. It's all about trade-offs. The choice between JANs, VAEs, and DDPMs really depends on what you need for a specific application. You might choose JANs for sharpness and speed, VAEs for stability and getting a nice structured concept space, or DDPMs if you absolutely need top-tier quality and diversity, and you can afford the slower generation time. Each represents a different philosophy for probabilistic data generation.
Okay, that's a great overview of the tools. So we've got the mathematical elegance of fractals, this language of self-similarity, and then we have the raw creative power of these deep generative AI models like JANs, VAEs, diffusion models. Now, here's where it gets really interesting, right? How do these two profound ideas actually come together? How do we get AI to generate fractal-like images? It seems like there may be two main paths, two distinct ways researchers are merging them.
Indeed, that's exactly right. There are two primary strategies emerging. The first path, and perhaps the most direct and foundational method, is what we can call data-driven approaches. Sometimes you'll also hear it called AI-enhanced fractal synthesis. The main thing produced here are often called pseudofractals. Now, that term is important.
Pseudofractals, meaning fake fractals.
Not exactly fake, but crucially, they are images that look like fractals. They capture the intricate visual style, the textures, the repeating patterns we associate with fractals. However, and this is the key distinction, they are not generated by executing the actual underlying fractal mathematics, those recursive rules we talked about earlier. Instead, these pseudofractals are the result of AI models learning the appearance and the stylistic characteristics of fractals from looking at a massive data set of actual fractal images. It's about the AI learning the visual look, not executing the mathematical process.
Okay, so the AI becomes an artist mimicking the fractal style, rather than a mathematician calculating it.
That's a pretty good analogy, yes. And the process for generating these pseudofractals follows a fairly standard structured machine learning pipeline. The very first, and honestly the most crucial step, is dataset generation and collection. You can't train an AI to mimic fractals without showing it lots of fractals first. So researchers algorithmically generate a large and importantly diverse dataset of actual mathematical fractal images. Think lots of examples of the Mandelbrot set, various Julia sets, maybe IFS fractals like the Sierpinski triangle, all generated with a wide range of structures, coloring, zoom levels, and parameters. The goal is to give the AI a really rich, varied visual library to learn from.
Makes sense. Garbage in, garbage out, right? You need good data.
Absolutely critical. Then, after collecting this data, the next vital stage is data preprocessing and augmentation. You need to get these images ready for the neural network. This usually involves normalization, which means scaling the pixel values maybe to be between 0 and 1 or NICMA 1 and 1. This just helps the training converge faster and more reliably. All the images also need to be resized to uniform dimensions, whatever the specific AI model requires as input.
And augmentation. Why do that if you've already got lots of fractals?
Data augmentation is super important for preventing the model from just memorizing the training examples. You apply techniques like random rotations, slight translations, maybe scaling them a bit, or flipping them horizontally or vertically. This artificially increases the variability in the dataset and forces the AI to learn the inherent structural properties of the fractals, regardless of their specific orientation or position in the image. It promotes generalization.
Okay, so you've got this big, clean, augmented data set of fractal images. What's next?
Now comes the core part, generative model training. You take a standard, deep generative model, typically a GAN or a VAE, though as we mentioned, diffusion models are increasingly strong candidates too, and you train it on this prepared data set. If you're using a GAN, remember the two networks. The generator learns to produce images that the discriminator classifies as real fractals, meaning it can't tell them apart from the training data. This adversarial process pushes the generator towards creating visually convincing pseudofractals.
And with a VAE?
With a VAE, the model learns that smooth, continuous probability distribution, that concept map representing the space of all fractals present in the dataset. This is particularly useful if you want to smoothly blend between different fractal styles or explore variations in a controlled way. So the main objective here with this data-driven approach is really twofold. First, create novel visual forms, these pseudofractals that still retain those essential visual properties we expect from fractals like apparent self-similarity and intricate detail. But second, and perhaps more creatively interesting, these pseudofractals should also incorporate unique variations, maybe new stylistic elements that are introduced by the AI's own complex learning process. It's not just copying. The AI might blend features or create textures that weren't explicitly in the training data but are statistically consistent with it. So this approach kind of bridges the gap between the strict deterministic rules of mathematical fractal generation and the more flexible, data-driven creativity of modern AI. It can lead to visual patterns and aesthetics that might be difficult to achieve just using the traditional math formulas.
Okay, so the AI learns the style. Once it's trained, how do you know if it actually did a good job? How do you analyze these pseudofractals?
Great question. Rigorous analysis of pseudofractals is key. It usually starts with careful visual inspection. Just looking closely at the generated images to see if they exhibit those hallmark fractal traits. Do you see repeating motifs? Do parts seem self-similar? Does it feel like a fractal? But subjective inspection isn't enough. You also need quantitative analysis. Researchers use techniques like the box counting method, which is a standard way to estimate fractal dimension on the generated images.
Calculating the fractal dimension of the AI's output.
Exactly. It gives a precise numerical measure of the image's complexity or roughness, which can then be compared to the fractal dimensions of the original mathematical fractals in the training set. It's a way to quantify if the AI captured that geometric aspect. But maybe the most fascinating part of the analysis is latent space exploration. This gives us really deep insights into how the model has internally organized its understanding, its representation of fractal concepts.
Exploring that concept map we talked about.
Precisely. For VAEs, because their latent space is designed to be smooth and continuous, you can do things like pick 2 points in that space, representing 2 different pseudofractals, and then smoothly interpolate between them. Watching the generated image smoothly transition from one fractal form to another reveals how the AI has learned this continuum of fractal aesthetics. It shows the structure of its internal understanding. For GANs, it's a bit different, but you can often perform vector arithmetic on their input noise vectors. By adding or subtracting these noise vectors, you can sometimes manipulate specific semantic features in the generated output in a surprisingly consistent way.
Like making it more spiky or more swirly.
Exactly. You might find a direction in the noise space that corresponds to spikiness or color palette or level of detail. Being able to control these high-level attributes offers a new level of artistic influence. So this kind of analysis provides profound insights into the model's learned abstractions about fractal structure, and critically, it points towards developing more controllable, more interactive fractal generation systems in the future, pushing the boundaries of human-AI collaborative art.
Okay, so that's one path. Train the AI to mimic the visual style of fractals based on data. Very cool. But then you mentioned this other path, maybe even more profound. That's about literally building fractal logic, that core idea of recursion and self-similarity directly into the AI's architecture itself, into its design. Now, that sounds really interesting. Moving beyond just imitation too, like fundamental integration, what does this actually mean for how the AI computes things?
Yes, this leads us to the second major category, architecturally driven approaches. And you're right, this is arguably a more profound, maybe even paradigm-shifting idea. Here, the ambition moves far beyond just getting the AI's output to look like fractals. The goal is to embed fractal principles like recursion and self-similarity directly into the model's fundamental structure, its very blueprint.
Building it into the network itself.
Exactly. This approach often draws deep inspiration from the recursive and self-similar patterns we see everywhere in nature. Think river networks branching or trees growing, or even how biological neural networks might be structured hierarchically. It's about trying to give the AI a more organic, emergent kind of intelligence, mirroring natural complexity. The core concept driving this is recursive modularity and self-similarity, but applied at the architectural level of the AI model. The central idea is to abstract an entire generative model, or a key part of it, into a reusable atomic generative module. This module isn't just a static component. Crucially, it has the ability to recursively invoke child modules of the same kind.
So the module calls itself, or copies of itself.
Essentially, yes. It creates this deep hierarchical framework where the overall structure exhibits self-similarity across different architectural levels, just like a mathematical fractal where the parts resemble the whole. And this recursive process leads to a really fascinating, almost counterintuitive outcome. You get an exponential growth in the model's expressive complexity and the level of detail it can potentially generate in its output, but with only a linear increase in the number of recursive levels or the depth of the recursion. It's a remarkably efficient way to build complexity, a kind of computational leverage.
That sounds powerful. So what does this architectural integration of fractal ideas actually mean for practical things, like computational power and speed? Does building this recursive logic directly into the model's structure offer real benefits in efficiency, especially when you're trying to generate very high-resolution, intricate images, where traditional methods often bog down?
That's one of the major selling points, yes. This architectural integration yields a significant, potentially transformative efficiency benefit. Models built this way, often called fractal generative models or FGMs, can be incredibly fast, especially when you're creating high-resolution images. The sources we looked at suggest a staggering potential speedup. We're talking about models that could be, for instance, something like 96 times faster than a comparable traditional pixel-by-pixel visual autoregressive VAR model when generating images at, say, 256 by 256 resolution.
Wow, 96 times faster. How does that work?
It stems from a clever divide-and-conquer strategy that's inherent in their recursive design. The FGM hierarchically breaks down the task of generating the image. It might generate a coarse, low-resolution version first, and then recursively generate finer details within patches of that image. A key technical factor driving this efficiency relates to the attention mechanism within each module that's the part of the network that decides which other parts of the image or data are most relevant to generating the current pixel or patch. In these FGMs, the attention calculation is typically computed locally, only over these relatively small patches, rather than globally across the entire, potentially huge image. This localized attention dramatically reduces the computational burden, avoiding the quadratic scaling cost that often makes traditional autoregressive models very slow for large images.
So local attention is the key to speed.
It's a major factor, yes. And researchers like Tianhong Li and colleagues were instrumental in introducing and demonstrating these specific fractal generative models. Now, in terms of actual performance and, of course, limitations, nothing's perfect. FGMs have shown some strong capabilities. They demonstrate really strong performance and likelihood estimation. They've achieved state-of-the-art negative log likelihood NLL scores on benchmark datasets like CFAR10. That basically means they are very good at accurately modeling the underlying probability distribution of the data. They learn the patterns well. They also produce generally high-quality images on more complex benchmarks like ImageNet, showcasing their generative strength. Another plus is that their architectural design often allows for more direct, maybe more interpretable, pixel-level generation and editing tasks. Things like image in-painting, filling in missing parts realistically, or outpainting, extending an image beyond its original borders can sometimes be handled quite naturally by their structure, offering a level of control that can be harder to achieve with other types of models.
Okay, sounds impressive. But what about the downsides? Where do they fall short?
Well, despite these strengths, their overall generation quality, particularly when measured by the standard perceptual metrics like FID, Frisch inception distance, and IS, inception score, doesn't yet consistently surpass the results from the absolute top-tier GANs or the latest diffusion models. They're competitive, but maybe not quite leading the pack on those specific metrics. Some critical reviews also suggest that while FGMs are undeniably highly efficient and represent a clever acceleration technique, they might perhaps be viewed more as sophisticated, optimized versions of existing visual autoregressive models, rather than representing a completely revolutionary new architectural paradigm. And there's also a question of whether they can capture the full diversity of the training data quite as effectively as, say, diffusion models, although they are generally better than basic autoregressive models in this regard. So promising, very fast, but still evolving.
Okay, so we've explored these really incredible ways that fractals and AI are merging, creating these stunningly intricate and often novel visual forms, both through mimicking style and through architectural integration. But surely, like with any cutting-edge scientific frontier, there have got to be some serious hurdles, right? Some formidable challenges that researchers are really grappling with, things that prevent seamless integration or widespread use. What stands out as a really significant computational barrier here?
You're absolutely right. There are definitely formidable hurdles. And one of the most significant computational challenges is something known as the fractal inverse problem.
The inverse problem.
Yeah.
Sounds ominous.
It's definitely tricky. To understand it, let's first quickly recap the forward problem. That's where you're given the simple mathematical rules, maybe the parameters for an iterated function system, IFS, and you use those rules to generate the complex fractal image. That's relatively straightforward. The inverse problem is precisely the reverse. You start with an existing fractal image, maybe one found in nature or generated by some unknown process, and your task is to work backward to figure out the exact simple mathematical rules, like the specific IFS parameters, the transformations, the probabilities that could have generated that specific image.
So looking at the picture and trying to deduce the recipe.
Exactly. Formally, it's framed as an optimization problem. You're trying to find the set of IFS parameters whose resulting fractal shape, its attractor, is as close as possible, minimizes the difference or distance to your target image. The core difficulty, and the reason it remains such a persistent and deep challenge, lies in its inherent computational complexity. This problem, finding the optimal IFS for a given image, has been formally proven to be NP-hard.
NP-hard. Okay, I know that means basically really, really hard computationally.
That's the gist of it, yes. In practical terms, it means there's no known efficient algorithm that can guarantee finding the absolute perfect optimal set of generating rules for reasonably complex fractals within a polynomial timeframe. The search space, the set of all possible IFS rules you have to check, grows exponentially with the complexity of the target fractal. So an exhaustive brute force search becomes computationally intractable, impossible for all but the very simplest cases.
So you can't just solve it directly?
Not in general, no. This theoretical intractability forces researchers to rely on heuristic or approximation algorithms methods that aim for good enough solutions rather than guaranteeing the absolute best one. It's like having a masterful symphony recording, but no easy way to perfectly reconstruct the composer's original score just by listening. This really limits our ability to, say, automatically extract the fractal recipe from natural patterns for AI to use.
Okay, so if finding the perfect answer is NP hard, basically impossible for complex cases, how do people actually try to tackle this inverse problem? What are these approximation approaches you mentioned?
Right, since a perfect, guaranteed solution is off the table, current approaches focus on finding good approximations using various optimization techniques. One prominent method involves genetic algorithms, or GAs.
Inspired by evolution, right?
Exactly. GAs are meta-heuristic search algorithms inspired by natural selection. They work by maintaining a population of candidate solutions, in this case, candidate sets of IFS parameters. This population then evolves over many generations. Solutions are selected based on how well the fractal they generate matches the target image, their fitness. They undergo processes like crossover, where parts of two good solutions are combined to create offspring, and mutation, where small, random changes are introduced. The goal is to iteratively improve the population, minimizing the error often measured by root mean square, RMS, or mean squared error, MSE, between the target image and the fractal generated by the evolving IFS code.
So it's like breeding fractal recipes.
That's a good way to think about it. Another powerful technique used is simulated annealing, or SA. This method draws an analogy from metallurgy, specifically the process of annealing metal, where you heat it up and then cool it down very slowly to remove defects and reach a strong, stable, crystalline state.
How does that apply here?
Well, the algorithm explores the vast space of possible IFS solutions probabilistically. It always accepts moves to better solutions, lower error. But crucially, especially early on when the temperature is high, it also sometimes accepts moves to worse solutions. The probability of accepting a worse move decreases over time as the temperature cools. This ability to occasionally take steps backward allows the algorithm to escape from getting stuck in poor local minima and hopefully find a much better, perhaps even globally optimal, solution overall. Again, the objective function it's trying to minimize is typically the MSE between the generated fractal and the target.
Interesting. Are there other approaches too, like using neural networks directly?
Yes, more recently, neural network approaches have emerged as well. Researchers have trained convolutional neural networks, CNNs, which are great at image analysis, to try and directly predict the IFS parameters just by looking at the input fractal image. Now, these predictions are generally approximate, not perfectly accurate, but they can be generated very, very quickly, much faster than running a GA or SA optimization. So they can serve as excellent initial guesses or starting points, which can then be further refined using those other optimization methods like GA or SA. It's a way to jumpstart the search. And finally, there's a theoretical tool called the collage theorem that's relevant here. It doesn't directly solve the problem, but it helps frame it. It basically states that if you can find a set of contractive transformations such that the union of the transformed copies of your target image forms a good approximation, a collage of the target image itself, then the attractor of the IFS defined by those transformations will also be close to the target image.
So finding the right way to paste copies of the image onto itself gives you the code.
In essence, yes, it transforms the problem from finding the attractor to finding the right collage, but finding that optimal collage is still a difficult search problem in itself, so lots of different angles, but still fundamentally a hard problem.
Okay, that makes sense. It's a tough computational nut to crack.
Yeah.
Let's shift gears slightly. Even if we can generate these amazing fractal hybrid images using either the data-driven or the architectural approach, how do we even know if they're any good?
Yeah.
Or if they're accurate fractals, or if the AI is truly capturing that underlying fractal essence? What really stands out to you about how we currently measure the success of AI image generation in general, and why is that whole evaluation approach potentially problematic when we apply it to the unique recursive geometry of fractals? It sounds like there might be a fundamental measurement mismatch going on.
You've absolutely hit upon a truly critical and maybe underappreciated challenge in this specific niche. The profound absence of adequate evaluation methodologies tailored for fractals. The current metrics we typically use for generative models, which were developed primarily with the goal of achieving photorealism, are almost entirely ill-equipped to capture or quantify the unique geometric structures and aesthetic properties that actually define fractals. This creates a really significant gap in our ability to rigorously assess the quality, the fidelity, and even the fractalness of these hybrid image generation systems.
So the tools we use to judge AI art are just wrong for this kind of art?
Largely, yes. The inadequacy of these standard metrics is quite stark when you think about it. Metrics like peak signal-to-noise ratio, PSNR, or structural similarity index are often used to compare an output image to a ground truth, measuring pixel-level differences or structural similarities. They're okay for tasks like image compression or restoration. Then you have metrics like inception score, IS, and more commonly now, fresh shape inception distance, FID. These are designed to assess the quality and diversity of images generated by models trained on large data sets of natural images like ImageNet. They basically use a pre-trained image classification network to judge if the generated images look real and cover a diverse range of recognizable objects.
And the problem is,
the crucial mismatch is that these metrics, especially FID and IS, simply do not care about, nor are they designed to measure, the unique geometric properties that are fundamental to fractals. They don't assess true mathematical self-similarity or infinite recursive detail, or the fractal dimension we discussed earlier. They're looking for realism and semantic diversity in the context of photographs. Let me give you a stark example to illustrate this fundamental mismatch. Imagine a generative model produces a synthetically flawless, photorealistic image, maybe a perfect picture of a cat that never existed. It might achieve an excellent FID score because its features align perfectly with what the underlying classification network expects from a real photo of a cat.
okay, good FID score.
Right. But that image obviously bears absolutely no resemblance to a fractal. Now, conversely, consider a mathematically perfect rendering of the Mandelbrot set with all its stunning self-similarity and infinite detail. That image might actually receive a poor FID score.
Why would it score poorly?
Because its highly structured, purely mathematical, recursive geometry is entirely alien to the distribution of natural images, like cats, dogs, cars, that the FID metric's underlying network was trained on. The metric essentially says, this doesn't look like a typical photograph, and penalizes it. This highlights a fundamental conflict. The metrics are optimizing for photorealism, while we're interested in geometric structure and complexity.
Wow, okay, so the standard measuring sticks are just completely misaligned with the goal here.
Exactly. And furthermore, there's another significant oversight: the pervasive lack of perception-based evaluation in these standard metrics. Existing quantitative measures completely fail to capture how human observers actually perceive and cognitively process these incredibly intricate, often visually dense and complex fractal patterns. These metrics entirely disregard the concept of cognitive load. That's the mental effort required for a person to process incoming information.
Cognitive load, how hard your brain has to work to understand the image.
Precisely. A highly detailed fractal image, just by its very nature, imposes a substantial intrinsic cognitive load because of its inherent complexity. There's just a lot going on. But current metrics offer absolutely no insight into whether this complexity is presented effectively, or if the visual design itself adds unnecessary extraneous load mental effort caused by poor presentation rather than the content itself. Is the image clear despite its complexity, or is it just a confusing mess? The metrics can't tell us. This profound gap really underscores the urgent need for entirely new evaluation frameworks, ones that go beyond simple pixel statistics or photorealism scores and instead incorporate rigorous measures of the actual geometric structure and the nuanced principles of human visual perception and cognition.
Okay, so standard metrics are out. What's the solution then? What kind of new evaluation tools do we need for this field?
This situation really points to an urgent need to develop a whole new, purpose-built suite of fractal-specific evaluation metrics. And it needs to be multifaceted, looking at the problem from different angles. Firstly, we definitely need robust geometric metrics. These would be algorithms specifically designed to run on the generated images and automatically calculate properties like the fractal dimension, maybe using that box counting method or similar techniques. We also need ways to measure statistical self-similarity across different scales within the image. These provide quantitative validation of the output's fractalness.
So metrics that actually understand fractal geometry.
Exactly. Secondly, and this is crucial but often overlooked, we need perceptual and cognitive metrics. This means moving beyond algorithms and conducting meticulously designed user studies. These studies need to be rigorously grounded in cognitive psychology principles to evaluate aspects like the perceived aesthetic appeal of the generated fractals, their judged visual complexity, and critically, the actual cognitive load they impose on a human viewer. How easy or difficult are they to process visually? Do people find them engaging or overwhelming?
Getting human feedback into the loop.
Absolutely essential for understanding the subjective quality. And lastly, especially as these models become more sophisticated, we need controllability metrics. If the goal is often to create systems where users can guide the generation process, maybe asking for a spikier fractal or one with more spirals, then we need quantitative measures to assess how effectively and precisely the model can actually manipulate these specific, user-defined semantic attributes in its output. How well can we steer the generation?
Okay, so geometric, perceptual, and controllability metrics. That sounds much more comprehensive.
It would be. And complementing the development of these new metrics, another absolutely essential step for the field is the creation of a large-scale fractal hybrid benchmark dataset. This wouldn't just be raw images. It would need to contain a diverse collection of mathematically generated fractals where we know their exact generating parameters, alongside a carefully curated corpus of natural images that exhibit clear fractal characteristics like ferns, coastlines, etc. And critically, all these images would need to be meticulously annotated with both their geometric properties, like calculated fractal dimension, and a rich set of semantic labels describing their features.
A standardized test set for everyone to use.
Precisely. Such a benchmark resource is absolutely critical for enabling reproducible research, for fairly comparing different generative models and techniques, and for rigorously evaluating progress using those new metrics we just discussed. It provides a common ground for the entire research community.
Got it. So we've navigated the tricky technical terrain, the computational challenges like the inverse problem, and these complex measurement and evaluation issues. But beyond the purely computational and analytical complexities, you mentioned earlier that there are also these bigger societal questions swirling around AI-generated art, and especially these fractal hybrid creations. What does our deep dive reveal about the intertwined legal and ethical dimensions that researchers, developers, and artists must really grapple with as this field continues its rapid evolution? Feels like a whole other can of worms.
Oh, it absolutely is. The field undeniably faces significant legal and ethical dimensions that are, in many ways, just as intricate and complex as the fractals themselves. These issues often challenge long-established legal doctrines and societal norms, demanding really novel interpretations and careful consideration. One of the most prominent and currently contentious issues revolves around copyright and the fundamental human authorship doctrine.
Right, the question of who owns AI art.
Exactly. Current copyright law, particularly in the United States, and this has been significantly shaped by landmark cases like Tyler v. Perlmutter involving the U.S. Copyright Office, generally requires demonstrable human authorship for a work to be eligible for copyright protection. The law is built around the idea of a human creator.
So what does that mean for art made entirely by an AI?
That's the multi-million-dollar question right now. The implication is that purely AI-generated art, works created autonomously by an AI system without a direct, significant creative contribution from a specific human author, might simply fall into the public domain. They might not be protectable by copyright at all.
Public domain, wow. That could have huge consequences.
Huge. It's a major point of discussion and legal uncertainty right now because it could severely disincentivize the creation and especially the commercialization of purely AI-generated art if creators or the companies developing the AI cannot legally protect their output from unrestricted copying and use by others. Now, for AI-assisted works where a human is clearly involved in the creative process using AI tools, the situation is a bit different, but still complex. Copyrightability is typically granted, but only to the extent of the human's discernible creative contribution.
Meaning the human has to do more than just type a prompt.
Generally, yes. The U.S. Copyright Office guidance suggests it requires significant creative control over the final work's expression. This likely involves more substantive human involvement, for example, in the iterative selection, the arrangement, the modification, or the curation of the AI-generated elements to meet a specific creative vision. Just providing a simple prompt might not be enough to claim authorship over the output. It's about the level and nature of human intervention.
That sounds like a tricky line to draw legally.
It's incredibly tricky and likely to be tested further in courts. And intertwined with this authorship question are the ongoing and very heated debates, plus a growing number of high-profile mass copyright infringement lawsuits surrounding the use of copyrighted material within the massive datasets used to train these powerful generative models in the first place.
The training data issue. That's a big one.
It's massive. Artists, writers, photographers, musicians, and other rights holders are contending that scraping their work from the internet without permission or compensation to train commercial AI models constitutes large-scale copyright infringement. The AI companies, on the other hand, frequently counter with a fair use argument. They assert that their use of the data is transformative, creating something new rather than just copying, and that it doesn't unduly harm the market for the original works. They argue it's necessary for innovation.
And the courts haven't fully decided this yet.
Not definitively, no. The ultimate legal outcome of these complex, high-stakes cases will undoubtedly have a monumental impact on the future trajectory, the legality, and the economic viability of the entire generative AI field. Key players in shaping this include figures like Stephen Thaler, who keeps challenging the human authorship requirement, government bodies like the U.S. Copyright Office, represented by figures like Shira Perlmutter, who are trying to interpret existing law for this new technology, and of course the courts themselves.
Okay, so copyright is a minefield. What about other legal or ethical concerns? You mentioned privacy.
Yes, beyond copyright, data privacy presents another set of significant challenges. As we just discussed, training these deep generative models often involves scraping and processing absolutely massive data sets. While the focus is often on copyrighted material, these data sets can also inadvertently include personal information, images of identifiable individuals, or other sensitive data scraped from the web. This raises substantial concerns about privacy implications and the ethical sourcing and use of this data.
And there are regulations about this, right? So, like GDPR.
Exactly. Regulations like the General Data Protection Regulation, GDPR, in Europe and the California Consumer Privacy Act, CCPA, impose stringent requirements on how personal data is handled. These include needing a lawful basis for processing data, adhering to principles like data minimization, only collecting what's necessary, and crucially, honoring data subject rights. One particularly challenging right is the right to erasure, sometimes called the right to be forgotten. Individuals have the right to request that their personal data be deleted.
How is that a technical problem for AI?
Well, once data has been used to train a complex, deep neural network, it becomes deeply interwoven into the model's parameters and millions or billions of synaptic weights. It's not like deleting a record from a simple database. Figuring out how to effectively unlearn or remove the influence of a specific individual's data from a fully trained model without retraining the entire thing, which is incredibly expensive, is a very difficult and largely unsolved technical problem. This creates a fundamental tension between legal privacy rights and the current architectural realities of deep learning.
Wow, okay. So we have copyright battles, privacy challenges. Are there broader ethical guidelines people are looking at?
Absolutely. If we zoom out, the development and deployment of generative AI, including in the fractal art space, must also adhere to broader ethical considerations. While there isn't one single universally adopted code yet, we can look to analogous models for guidance. For instance, the ethical guidelines put forth by professional organizations like the American Psychological Association, APA, regarding the use of AI in psychological assessment and practice offer a really valuable framework.
How do psychology guidelines apply here?
The principles translate remarkably well. Key tenets from guidelines like the APA's include ensuring robust confidentiality and data privacy, which we just discussed, actively addressing and mitigating potential bias and fairness issues because AI models trained on biased data can, and often do, perpetuate and even amplify those societal biases in their outputs, promoting radical transparency and explainability, trying to move away from the black box problem where we don't understand why an AI makes a certain decision or generates a particular output, and critically maintaining human oversight and judgment. The overarching principle, which applies just as much to creative AI as to AI in psychology or medicine, is that AI should be designed and used to augment human capabilities, creativity, and decision-making, not to outright replace professional human judgment or creative insight without scrutiny. It's about keeping the human element central and responsible within the creative or analytical hierarchy.
That's a really helpful perspective. So, okay, we've laid out the fundamental concepts, the beauty of fractals, the power of generative AI. We've explored how they merge through data mimicry and architectural embedding. And we've confronted these really significant multifaceted challenges, the computational hardness, the evaluation crisis, the profound legal and ethical dilemmas. Given all of that, what does the future actually hold for this field of fractal hybrid AI image generation? Where is this all heading? What does the research roadmap look like for pushing the boundaries of this fascinating intersection? What should we be watching out for?
That's the exciting part looking ahead. The future of fractal hybrid AI image generation is really being shaped by a dynamic, multi-pronged research roadmap, focusing on several key areas for potentially profound advancement. Firstly, a really crucial and challenging pursuit is advancing semantic fractal correspondence. This is all about bridging that significant gap we touched on earlier, the gap between the low-level, often unintuitive mathematical parameters that define a fractal, like specific IFS coefficients or Julius at C values, and the high-level, human-understandable semantic features we use to describe them aesthetically, things like branch density or level of curliness or the presence of spiral motifs.
So making it easier for artists to control the output using natural language or concepts.
Exactly. The ultimate ambitious goal is to enable intuitive, high-level control. Imagine an artist saying, generate a fractal that feels more organic and less jagged, and the AI understands how to translate that semantic request into the precise underlying mathematical or architectural adjustments needed. How do we get there? Well, approaches include more intensive research into latent space disentanglement and interpretation within VAEs and GEMs. The idea is to try and make individual dimensions or directions within that learned concept space correspond directly to specific controllable semantic attributes. Researchers are also exploring how to leverage existing knowledge from computer vision about analyzing fractal features to help guide the generation process. And there are even more speculative, forward-looking frameworks being proposed, sometimes termed things like spectral fractal symbolic interfaces, which imagine ways to directly connect properties of the neural network's activity or structure to abstract symbolic meaning, allowing for a potentially much deeper, almost synesthetic level of control over the generated fractal forms.
Wow, okay. Deeper semantic control. What else? What about the AI architectures themselves?
Right. The second major area is architectural innovation. Building on that foundational work of fractal generative models, FGMs, that embed recursion, future research needs to vigorously explore using other cutting-edge generative architectures as the recursive building blocks the atomic modules. So this means actively developing and testing concepts like fractal diffusion models, or fractal VAEs. The idea would be to ingeniously combine the inherent computational efficiency that comes from fractal-like recursive structures with the distinct strengths of these other powerful generative paradigms, like the unmatched sample quality of diffusion models or the stable, semantically rich latent spaces of VAEs.
Mixing and matching the best architectural ideas.
Precisely. And perhaps even more ambitiously, there's a drive towards developing true hybrid architectures. These would be systems designed from the ground up to explicitly and seamlessly combine both the data-driven approach, learning from examples, and the architecturally driven approach, embedding fractal logic. Imagine, for instance, training a fractal generative model, FGM, not to generate pixels directly, but to operate within the learned, semantically meaningful latent space of a pre-trained VAE. Such a hybrid could potentially offer the best of both worlds. Highly structured, efficient generation, thanks to the FGM architecture, combined with a deep, learned semantic understanding of the visual concept it's synthesizing, thanks to the VAE's latent space.
That sounds incredibly powerful. What about the evaluation problem we discussed?
That's the third critical pillar. Establishing unified evaluation frameworks. This requires a dedicated, probably collaborative effort across the research community to develop that new, comprehensive suite of fractal-specific evaluation metrics we talked about. Just to reiterate, this absolutely must include robust geometric measures like automated fractal dimension calculation, self-similarity analysis. It needs perceptual and cognitive metrics derived from rigorous user studies evaluating aesthetics, complexity, cognitive load, and it needs controllability metrics to quantify how well users can actually direct the generation process. And complementing this, as we said, is the essential step of creating and curating that large-scale fractal hybrid benchmark dataset. Having that standardized dataset with mathematical fractals, known parameters, natural fractals, and rich annotations, geometric and semantic, is absolutely fundamental for allowing fair comparisons, tracking progress, and driving the field forward in a rigorous way.
Makes perfect sense. You need the right tools and the right benchmarks. Anything else on the roadmap?
Two more key areas. Fourthly, there's a renewed impetus on addressing the inverse problem and potentially linking it to compression. That NP-hard challenge of finding the fractal recipe from an image isn't just a theoretical hurdle. Solving it, even approximately, could have practical benefits. The new angle is using modern generative models themselves to tackle it. The idea is to train a conditional generative model. Instead of inputting noise and getting an image, you'd input an image, and the model would be trained to output the likely IFS parameters, essentially, the highly compressed fractal code that could generate that image. The model's objective would be to produce a code whose corresponding fractal attractor minimizes the reconstruction error compared to the input image.
So AI learning to compress images into fractal formulas.
Potentially, yes. This innovative approach could fundamentally lead to a new generation of incredibly efficient AI-powered compression algorithms, particularly for images that have inherent fractal-like structures. It marries the pattern recognition power of deep learning with the mathematical elegance and compactness of fractal descriptions. And finally, but certainly not least, a crucial pathway involves proactively navigating the complex legal and ethical landscape with concrete technical solutions, not just philosophical debate. Research should focus on developing better explainable AI, SAT-I methods, specifically tailored for creative workflows. These methods could help meticulously document the degree and nature of human creative input versus the AI's contribution in generating a piece of art. This documentation could be vital evidence for supporting copyright claims for AI-assisted works under the current legal frameworks. It's about providing transparency into the collaborative process.
Using tech to clarify authorship.
Exactly. Furthermore, implementing robust systems for data provenance and watermarking is becoming increasingly critical. For provenance, this means creating transparent and verifiable mechanisms to trace the lineage of the data used to train models, helping to address concerns about the use of copyrighted or sensitive material. For watermarking, it involves developing invisible but resilient techniques to embed identifiers within AI-generated content. This helps distinguish AI output from human-created work, promoting transparency, enabling accountability, and potentially combating misinformation or misuse. And of course, proactive engagement also means continuing research into technically challenging areas like machine unlearning to better address data privacy rights, and ensuring that broader ethical considerations like bias mitigation, fairness, transparency, and meaningful human oversight are not just afterthoughts, but are meticulously integrated into the entire life cycle of generative AI development and deployment practices.
Wow, okay, what a deep dive that was. We've really covered a lot of ground. We've journeyed through the intricate, beautiful world of fractals, exploring their core ideas like self-similarity and how they're generated through recursive rules. Then we peel back the layers on deep generative models, understanding the mechanics, strengths, and weaknesses of GANs, VAEs, and the really powerful diffusion models. They're the really exciting part, how these two distinct disciplines are merging. We looked at the data-driven approach, where AI learns to mimic fractal styles, creating pseudofractals, and the more fundamental architecturally driven approach, like fractal generative models, which build recursion right into the AI's structure. And alongside that potential, we've squarely confronted the formidable challenges that researchers and practitioners face on this frontier. The sheer computational difficulty of the fractal inverse problem, the critical lack of appropriate evaluation metrics to measure success beyond just photorealism, and navigating those swirling, complex legal and ethical waters surrounding AI authorship, training data rights, and data privacy. It truly feels like a landscape of both immense creative potential and significant, still unresolved questions.
It absolutely is. And this whole deep dive, really, in its very exploration of how AI systems are learning not just to mimic, but potentially to fundamentally integrate a kind of fractal logic, a logic mirroring nature's own complex processes into their architecture. It raises a really important, maybe even provocative question for you, the listener, to perhaps ponder. As these systems generate patterns that increasingly reflect the profound complexity and self-organizing principles we see in the natural world, what truly new forms of intelligence, or perhaps even entirely novel modes of creativity, might actually emerge from the synthesis? Could we see something that genuinely transcends our current understanding of both?
That's a fascinating thought to end on. Think about that. Algorithms potentially processing information or generating novelty in a genuinely fractal recursive way. Could that lead to entirely new kinds of digital creativity? Maybe even new forms of comprehension or problem solving? Something truly interesting to mull over as this field continues to unfold, constantly pushing the boundaries of what we conceive of as both art and maybe even intelligence itself.